Hello everyone, continuation of this lecture 3 is static error constants. We know that the different inputs we have to consider here for the different error constants. Positional error constant, velocity error constant and acceleration error constant. So that can be given by a standard table type of systems 0, type 1, type 2 and corresponding inputs step input, ramp and acceleration, or we can call it as parabolic. So for step input, what is the equations? It is 1 divided by 1 plus kp. For ramp input is infinity, that is steady state error is infinity. For parabolic, if type 0 system, the steady state error is infinity. Like that for type 1, if you come to the type 1 system, then you have to consider an velocity error constants, which is for corresponding input ramp, you can observe here. So type 1 system, step input is 0, then parabolic input is infinity. So for type 2 system, if it is type 2 means we have to consider a parabolic input signal, the steady state error which is given by 1 over k. Clear? Parabolic with respect to acceleration error constant, ramp with respect to velocity error constant, step input with respect to positional error constants. Let us discuss with the problem. Find the steady state error of the system as shown in figure when the reference input is R of t. R of t is ramp. So A is delta of t, B is u of t, and C t into u of t. So this is the given problem. This is the block diagram which is given. Reduce the block diagram by applying elimination of feedback. So if you apply the elimination feedback, so you will get the block diagram become, or transfer function which is become, transfer function is equal to 5 divided by s plus 4 divided by 1 plus, because the feedback is connected to minus sign. 5 divided by s plus 4 into 2 divided by s plus 1. So 5 2s are 10. So this s plus 4 gets cancelled. S plus 1 will become 0. Then 5 divided by s plus 1 into s plus 4 plus 10. Clear? So that is the equation. To find the steady state error, we know that for ramp input, steady state error is given by limits s tends to 0 s into e of s. E of s is nothing but this is the transfer function. So using this transfer function, you have to find the values R of t. Steady state error for ramp input, that is you will get 0. Then steady state error for the unit step input, so that is given by s into corresponding equation. Then steady state error for the ramp with respect to parabolic. Parabolic means 1 over s square. Multiplied the transfer function with 1 over s square. So here directly we have to substitute the values. Here we can rearrange the equations. Again rearrange. So we get this is steady state error for parabolic, steady state error for unit step, steady state error for ramp. So let us discuss with the next problem. Find the steady state error of the system shown in figure when the reference input is R of t. So this ABC indicate find the steady state error for the corresponding input also. So we know that steady state error for the ramp input, limit s tends to 0, s into e of s. E of s, or else we can write g of s into h of s. So here to apply the values, put the values and apply the limits s tends to 0, you will get this value. Then R of t, second type of input step, and third is parabolic. You will get the equation. For the system shown in figure, determine the type of number means type of system, positional error constant and velocity error constants, and find the steady state error, ramp, step and parabolic. This is the given problem. You have to find the value of corresponding inputs. So to find the values, you have to continue with the same problem. We know that if you rearrange the equations, so 10 divided by s into s plus 5 divided by s into s plus 3. So we get the equation will become like this. Then if you observe the order of system, that is the first case type 1. Then you have to find the positional error constant. We know that the formula Kp equal to limits s tends to 0 g of s into h of s. So that equal to limits s tends to 0 s into 20 divided by s into s plus 5 s plus 3. Actually this is limits positional error. So we'll get infinity. Then velocity error constants. Apply the values. We'll get the corresponding value 20 by 5. Then steady state error for step input, which is given divided by ESS is equal to 1 over 1 plus kV. And for ramp, it is 1 by kV. Velocity error. kV is known from this equation 20 by 5. So it becomes 15 by 20. So then these are all the basic fundamental problems which belongs to the finding the steady state error. Now we shall move on to the Routh RH criteria. In the module 3, that is the part chapter 2 RH criteria, that is called as Routh Hurwitz criteria. So to obtain the Routh Hurwitz criteria, he has identified the technique to find the stability of system. So the general equation which is given by transfer function equal to is the standard equations. N of s means numerator and delta of s means a denominator. Or else you can give d is the denominator polynomial equation. So for every characteristic equations, you have to find the roots of characteristic equation. So if the roots are lies in the left half of S plane, then the system is stable. So this is left half of S plane. So this is right half of S plane. The plane is S plane, which consists of imaginary and y axis and real terms in the x axis. That is, we can call it as sigma or real term. For the system described by T of S, that is a transfer function to be stable, is the roots of characteristic equation which is lies in the left half of S plane. So from the procedure to determine the right half of S plane and imaginary roots of characteristics polynomial equation. This equation is called polynomial equations. Yeah. So using these methods to find the roots of characteristic equation. So to check the criteria of RH Routh methods, there are the two conditions. If any row of the Routh table can be multiplied by positive constant without changing the value of row below. To avoid the division of zeros, an epsilon is assigned to replace the zero in first column. That is, if zero is up here, then you have to find the value of roots. So this is the characteristic equation which is given by. In some test they are given as f of s, that is characteristic equation. So here you have to mark the assign the numbers. This is 4, 3, 2, 1 and 0. So in the first row, here order of s is s to the power of 4. So I will write that in decreasing order, that is column matrix. S to the power of 4, s cube, s square, s to the power 1, s power 0. In the first row elements, you have to enter the even numbers, even number of polynomial. 0, that is 4, 2 and 0. That is A0, A2, A4. Then you have to write the odd numbers 3, 1, A3, A1 and 0. Okay. So this is the initial steps as per the RH criteria. Then for those initial steps, you have to apply the Routh Hurwitz criteria. So just look at the table, you have to multiply like this. Okay. A4A1 minus A2 A3 divided by this A3. So we will get the values B1. Then you have to multiply A3 into A0 minus you have to write A3 into A0 minus A4 into 0. So that will be done in the next step. A4 into 0, A3 into A0 divided by A3 only. That is coefficient is called B2. Similarly, you have to write the A3 into 0 divided by 0. So we will get the second coefficient, then last coefficient. Okay. Step 2. Interrupt the root table to tell how many closed loop poles are in the left half of S plane and right half of S plane. So if the number of roots of polynomial that are right half of S plane is equal to number of sign changes in first column. This is the very important. So number of sign changes. Suppose here there are the number of columns. It is first value is plus, second value is plus, third value is minus, fourth value is again plus, fifth value is minus. So these two are common sign changes, plus plus, there is no difference. From this point you have to consider plus to minus, one sign changes, minus to plus, second time sign changes, plus to minus, again third time sign change. There are the three types or three times there will be sign changes in the column elements. Hence we have to decide that there are the three roots which are lies in the left half of S plane. That is the statement which denotes. Clear? Then you have to write the note. If the coefficient of characteristic equation are different algebraic, then the least right half of roots are examples. Okay. Definitely one or more right half of planes. So if the coefficient of the characteristic equation, if it is algebraic, then directly we can decide that one or more than one poles which is lies in the right half of S. If coefficient of characteristic equation having zero value, that is if you are putting S values zero value, there are the imaginary or RHP, right half of plane roots. That is example will be like this. So has imaginary axis roots indicate by missing S cube term. So if any of the term will be missing, then directly we can say it is will get negative value. Then that negative value is lies in the right half of S plane. So this is the examples. So for the system shown in figure, check the stability. So rewrite the equation as in standard form. So you will get the standard form equation. Then you have to write it in the tabular column. Here after consider this denominator polynomial. Write the equations. Here you can mark that. This is a naught. Here this is a1, this is a2, this is a3 as for the method. So a3 is 1, then a2, a4 is 0, 0, 31, 1. That is even number. Odd number is 1, 1030. 1 and 1030 is odd number. Okay, and 0. Cross multiply is 1 into 31 minus 1 into 103. Because here 10 is common factor, you have to take the 10 as common factor. Then if you are solving this means you will get the answer. Then find the root method, determine the stability of closed loop transfer function. Consider this denominator and you have to write the column. So here you have to observe it. So plus to minus, again minus to plus. There are the two sign changes in the left half column. Therefore the system has two right half of plane positive roots and hence it is unstable. So then you have to find the values, apply the root harvest criteria and find the value of it. This is very important. Okay. So write the values as 5, 1, A0, A0, A2, A4. So if I observe this, A0, A1, A2, A3, A4, A5, A0, A2, then A4, then A1, A1, A3 and A5. Now we have to multiply 13 into 54, 1 into 82 divided by 13. So we'll get the 47.7. How to get that means 13 into 54 minus 82 into 1 divided by 13. So we'll get this value. Then again same thing, 13 into 60 plus k into 1 minus 3k. So we'll get the values. Then you have to find the values by solving the equations. You will get the k value. K is solve this quadratic equation. Simplify this equation, you will get the value of k. If the k is positive, then the system is stable. If k is negative, system is unstable. This is one more example. So that will be discussed in the next session.